Hello, welcome to this week's Naked Scientists with me, Chris Smith, and with Dave Ansell.
Hello, and this week, what has the European Space Agency's Planck probe revealed about the birth of the universe? We get curious about the latest from the surface of Mars, and we hear about the new 3D screens that could be reaching your mobile soon.
Plus, we investigate what the future holds for digital data storage. How can we ensure that what we're recording today, on film, discs, or even up there in the cloud, remains readable for years to come?
If you'd like to get in touch with us here at The Naked Scientists, email chris@thenakedscientist.com, tweet @NakedScientists, or find us on Facebook.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, first, joining us to take a look at what has been making science headlines this week are science journalists Mark Peploe and Victoria Gill, and also Phil Broadwith. He's from the Chemistry World magazine. Now, Mark, you've been down to the European Space Agency's press conference today, where they've revealed what their Planck probe mission has been revealing about the early universe. What did you flush out?
Yeah, that's right. So the Planck Space Telescope has given us the most detailed map yet of the cosmic microwave background. That's the residual glow from the Big Bang that started it all off, the beginning of the universe.
Tell us a bit about the history of the mission.
Okay, so it was launched in 2009, and it actually builds on previous efforts to measure the cosmic microwave background radiation. And it's out there in space about 4 times as far away from the Earth as the Moon, far enough away from the Sun that its very, very cold sensors can detect the faint traces of microwaves coming from actually just 380,000 years after the Big Bang.
And what is it revealing?
It's already giving us a very detailed measure of the age and composition of the universe. And hopefully in a year's time, when all the data is in and analysed, it might actually give us more clues about the origins of the universe. What
was the big question that we needed Planck in order to be able to answer?
The key thing really was in looking at why the universe is as big as it is and why it looks the same everywhere. And to do that, you need to understand how quickly the universe expanded in just the first instant, the first 10 to the minus 32 seconds after it was born. And that's really what it's starting to probe now.
I don't want to pour cold water on all this, but one of our colleagues who has been talking to some people about this today, he said, I've just heard a distinguished professor of astronomy who will remain nameless say that the press conference reached heights of excitement that we haven't seen since the big speeches of John Major's premiership.
Yeah, it was a strange press conference. I think they actually struggled to work out exactly what the top line on this story should be, actually. And I think the reason for that is in a lot of the easiest to understand aspects of this are about how old the universe is. It's 13.82 billion years, by the way. How fast it's expanding, what it's made of. And these are slight adaptations on the information that we had already. And it's sort of confirmation of a lot of stuff that we kind of already knew. But the more exciting stuff, actually, is the stuff that's incredibly difficult to explain. And that's stuff about what happened in that first instant of the universe, why it expanded so rapidly, what was driving that. And it rules, the data that we've got from Planck basically rules out a lot of the guesstimates, the models that people had for how that works. And actually it's narrowing down on pretty much the simplest suggestion for how that inflation happened.
Victoria?
So I was wondering how far back exactly cosmic background radiation can take us. I'd heard that looking at this Planck data would even be able to peer before the Big Bang when there was nothing, as I sort of don't quite understand it. Like, how could it do that?
Well, there you go. Inflation, this process of very rapid expansion of the universe, was, like I said, invoked to explain why, for example, bits of the universe where you look in any direction, it pretty much looks the same. There's stars, there's gas. It's largely indistinguishable on the sort of large scale. So at some point, all these things must have been in very close together in a melting pot, almost like continents that have moved apart. And you can see the outlines of the coastline. That suggests that at some point they must have been together. So rewinding the universe, you have to say, well, at some point they must have been together, and to get them as far apart as they are now, there must have been some bloody great fast expansion at some point near the beginning. Where theorists have suggested that looking at the cosmic microwave background can take you before the universe is from those theorists who advocate an alternative to inflation, that rather than the Big Bang, there was a big bounce. Before the universe that we live in now, there was a previous universe that contracted, and all these points that we see that are all part of a big melting pot that all look the same, they all look the same because they were squished together from a previous universe. And that means you don't have to invoke this very rapid inflation. And there are signals in the Planck data that should tell us one way or another which one of these is the right model. Those, sadly, did not come out today. Early 2014. It's called the polarization data. It's going to tell us about B modes, and I'll leave it there.
We'll look forward to that, won't we? They're just holding a little bit back to make sure you're all back for part 2.
So, for something slightly different, I hear you've been getting into giant squid, Victoria.
Not getting into them, I hope. Just
I would fit 18 metres long. Yes, 43 of them that geneticists from the University of Copenhagen, their Natural History Museum, have been looking at. And basically, this study is the first genetic study to really tell us about this species, because since they were first described in almost 150 years ago, because they are so elusive, because they live in such deep waters, and only very, very few species have actually been caught, which is why this team only had 43 specimens from all over the globe to look at, most of which were found in the bellies of sperm whales, actually cut open sperm whales that had been beached and died, and found these giant squid inside. And they found that no matter where in the globe these giant squid come from, and they're from all over the place, Japan, off Europe, off the US, they're all the same species. They're all very, very genetically similar to each other.
So why did we think they were different? Did they look different in different places? And so they were just sort of in the same way as humans are all the same, except that we have slightly different appearances depending on where on the Earth's surface we live. Squid is sort of similar?
They do look quite different. That's the weird thing. I mean, first of all, you would think that they would be they might have sort of speciated, they might have divided up, because you find them so far apart, because these global populations that they found, and when I say populations, they've just found one specimen either accidentally when they've been trawling through the ocean, or they might have found one that's been washed up when it's died. They've seen them so far apart. They found them in Japan, they found them off the US, they found them as far south as Australia, so all over the world in all different waters of different temperatures as well. But they do look different in the different places that they've caught them. Apparently, the ones they've caught off Japan or found off Japan have been quite sort of stubby and rounded, and then the ones that they find a little bit further north in colder waters are sort of more elongated and kind of stringy. So they do look very different. The ones
outside Japan, is that pre-Fukushima or post?
The data didn't go that far, actually. I think pre and post, they're still quite chubby squid, apparently. But so they do look quite different colours and kind of different shapes, but it seems that they're all one species, no matter where in the world they're found. So they think that they're just dispersing all over the globe, just drifting on the ocean currents.
How elusive are these things, Vic? How often do we actually come up with a sample, a giant squid, to actually dissect and genome sequence?
Well, see, that's the strange thing about them. Just because they live in such deep water, they live in the deep ocean, and so we really haven't seen or found very many of them at all. Like I say, there were just 43 species, and it was 150 years ago that this species was first described from a specimen by this Danish naturalist, and yet we've only got 43 species that these guys could get genetic data from, so it kind of shows you how few we found. But in actual fact, they think that because they find them in the bellies of sperm whales, and because sperm whales do seem to feed on these animals, they seem to provide them with a decent amount of food, that the population's actually quite big. And it's just that where the mature squid live once they get big and they dive to the deep ocean, which is probably where they mate and they reproduce, but nobody's ever seen that because they live in these just incredibly hard to reach places. But they think there's a big population down there and they just don't really see them that often.
So was there any idea whether the different shapes and colours of them in different places was because they were separate populations, or because in different temperatures they took on different shapes and different colours or whatever?
Yeah, that's a really good question. And I think this is what some of the genetics is telling us. So these guys have looked at mitochondrial DNA, which is the DNA contained in the little energy-producing packets or little factories within cells. And it's inherited down the maternal line, so it gives the biologists a really good idea of just how closely related these animals are. And because they know now that they can pin down that, yes, we have just one species of giant squid for all the specimens we've found in the last century and a half, then there must be different reasons for why they're taking on different shapes and forms, and you can kind of attribute that to environment and diet and do further studies, but you can eliminate the genetic differences because they've done the biology to figure that out now.
Well, back into outer space, or sort of, Mars. And Phil, you've been taking a look at the Curiosity data. Tell us more.
Well, yes, Chris, you could say that it's one small drill for a rover and one giant scoop for mankind.
Very nice. OK, and what have they found in this? This is Curiosity scooping up bits of Martian soil and analysing it, of course.
Yes, so the Curiosity rover's been up on Mars since sort of October of last year, and it's been doing various experiments, but the latest one that we've got the data back is where it's drilled into the ground using it has a drill mounted, and then it has a little scoops up the rock that it's drilled, feeds it into its analytical equipment, and what it's found is that in a dried up either lake or river, what looks like a dried up lake or riverbed, there is rock that could have supported life. We say it could have supported life in that it is made from igneous rock, molten rock coming up from underneath the surface, mixing with water, which gives us a clay mineral that it's very similar to ones that we've found in other places that we know form that way. It also has calcium sulfate in it, which indicates that the water that found that it was either neutral or slightly alkaline and not very salty, and those are exactly the kind of conditions that could support microbial life.
So the environment looks good, but they've yet to say, hey, look, we found the compounds that are life.
Yeah, absolutely. All we're saying at the moment is that the environment could have supported life. There's still no evidence of life. Previous data, they have found some evidence for some organic compounds. So again, that's again pointing in the right direction. But again, there's still no direct evidence of life.
I guess with organic compounds, they could have just come from comets, because comets are known to have organic compounds in them.
Yes, exactly right. Comets or other things striking, other objects coming into the planet from out in space. So they can be brought in a variety of different ways, and there is certain chemistry that can go on in the soil. There's often perchlorate in the soil, which is very highly oxidized. So if you've got carbon compounds, you can build complexity just by doing chemical reactions by light and the perchlorate and various other things as well.
Where's Curiosity going to head next? Because at the moment it's been keeping fairly close to its landing site. What's its ultimate destination?
They want to go to a place called Mount Sharp or Aurelis Mons. I think that's the right pronunciation. And it's actually still quite a long way away from there at the moment. It's only moved, I think it's a matter of hundreds of metres, if that, so far. And the place that they're trying to get to is, I can't remember exactly how far away, but it's many, many times that. So they've got to really get a move on if they want to make that before the end of the official mission date.
Yeah, when is the Curiosity supposed to end? Because the last set of rovers, of course, are still going, aren't they? So that's been a very long mission, well beyond its mission end date. So this one, it was not just for one season, is it?
As far as I remember, they're about a third of the way through the official mission length already, which, given how far they've got in that time, if they carry on at the same rate, then they're not going to get anywhere near to Mount Sharp. So they need to kind of pick up the pace a little bit now.
So get a move on Curiosity. Thank you, Phil. And Dave, you've been taking a look at a way to repair blind eyes, potentially in future.
That's right. Scientists from the Italian Institute of Technology in Genova have managed to stimulate a rat retina just by using a piece of plastic and some light. So there are quite a lot of diseases which cause degeneration of your retina, things like retinitis pigmentosa and macular degeneration, which are very common, especially in elderly people. And whereby your retina can't detect light, so you essentially go blind.
So critically in those conditions, the photoreceptors that convert photons into nerve signals, they go, but the actual retina parts that give rise to the optic nerve going back to the brain, they're still there.
So the wiring's still there. So the idea is that if you can somehow put the signal into that wiring, you could still see. So what they've been doing is they've been dealing with a series of plastics which, when you shine light on them, they can produce voltages. And they've got a sheet of this plastic called P3HT. And they've discovered that if you put a piece of retina on the top in a kind of sort of salty liquid electrolyte on the surface, and then you shine a light at the plastic, you get enough voltage produced by the plastic to trigger these cells. And depending on how fast you shine that light, if you're shining it at 1 hertz, so flashing on and off once a second, about 95% of the time when you shine it on, you trigger the nerve cells. If you're shining it at 20 hertz, 20 times a second, it gets a bit less good, 65% of the time. So it's not perfect, but it does show that just with a very, very simple thing, just a sheet of plastic and on top of a retina, you can actually produce signals which should then, if the retina was still attached to the rat, mean the rat could see.
Does enough light go into the eye to drive this thing, were you to implant this into the eye as a sort of implant?
So at the moment, there's enough light getting there, and it would be stimulated by full sunlight, so you'd be able to see in full daylight. But as soon as you got into inside and lower light levels, it's not very good. So as it is at the moment, it probably wouldn't be an ideal solution, but that's something which I'm sure they're looking into developing and increasing the sensitivity and increasing the effectiveness of the stimulation.
What I was going to say, Dave, is you said they have to put a sort of salty solution on the top. Is the eventual idea to have that supplied by the fluid inside the eye?
Yeah, so you're essentially filled with salty solutions, and so the idea, I think their idea is, and what they're looking at doing next is basically just taking a piece of this plastic, putting it in the eye of a blind rat, and seeing whether the rat can then detect light. It has the advantage over other systems where they've actually used complex electronics, in that it is just a sheet of plastic. It doesn't need any power. It doesn't produce any heat. And this plastic also seems to be fairly biocompatible. They've certainly grown nerve cells on it for 20 days, and the nerve cells seem perfectly happy. So obviously it's a long way until you actually use it in humans, but it's looking quite positive.
Well, I've got an item here which is in Science Translational Medicine this week. This is Sanjeev Gambhir and his colleagues. They're from Stanford. This caught my eye because it offers us an opportunity to non-invasively study where stem cells go in the body when you use them. Because one of the big questions therapeutically about stem cells is we're very happy to put them in, but then we can't really ever trace where those cells went and in what sorts of numbers in order to marry up clinical outcomes with the behaviour of the cells, at least until the person dies. And then you can get the cells back out again. So this is a big problem which is really hampering our ability to do these sorts of studies at the moment. And so what this group have done is to come up with a way of labelling cells with nanoparticles which can be detected by ultrasound, by MRI, and they're fluorescent as well, so that it doesn't matter what sample you've got, you can find these cells and you can count them as well, because the ultrasound signal makes them quantifiable.
So even if they were somehow being excreted, you can find them by looking even just for the fluorescence there?
They shouldn't actually be excreted in any great number, because what they do, if you're going to use, say, stem cells for heart attack treatment, and they've done experiments in rats to test this, you incubate the stem cells with these tiny silica nanoparticles, and the cells take up the nanoparticles. They appear to be completely harmless to the stem cells, but then you put them into the tissue, and in this case they inject them into some rat hearts, and then they follow them up for days to weeks afterwards, and they can detect, the limit of detection with ultrasound, they say, is about 70,000 cells, which is actually not that many. It sounds like a lot, but in the terms of a therapeutic dose, that's not very many.
One thing which strikes me is that a stem cell, the point of it is it will split and grow into lots more cells. So surely you've only got a limited number of these nanoparticles. Will they get spread out and diluted to the point they won't work anymore?
Yeah, they looked at that in the paper, actually. That's a very good question. And they didn't find this was too much of a problem, actually, because if you've got a lot of them in the cell to start with, even taking into account a few divisions, because the cells divide a bit but not a huge amount, because as soon as they go into the target tissue, they do what's called differentiate and become more specialist, probably in response to local signals in the tissue. So they do divide a bit, but not a huge amount, and so the dilution effect doesn't appear to be a major problem. I think it's more that you've got a safe marker that can be detected in numerous different ways, and this means they can now begin to marry up data on where they put the cells with how they appear to have behaved and what the eventual outcome was, in order to optimise these sorts of treatments in patients.
Brilliant.
Thank you very much to Mark Peplow, Victoria Gill and Phil Broadwith. And you can find out some more information, including the references to the papers that we've been discussing and some write-ups of the stories, on our website at thenakedscientist.com/news.
This is The Naked Scientist with me, Dave Ansell, and Chris Smith. If you'd like to get in touch with any questions or comments, email chris@thenakedscientist.com, tweet @nakedscientists, or find us on Facebook.
3D screens in TVs and portable games consoles like Nintendo 3DSs have been around for quite a while, but they're limited because you have to look at them from a fixed position. And if you don't want to sit around with 3D glasses on, which is the alternative for most current 3D TVs, your options are really quite limited. But now a team from HP's research labs think that they might have solved the problem.
We're joined by one of the team members, David Fatal, to find out more. So, David, how do current 3D displays work?
There's a host of solutions for a 3D display out there already, on the commercial market. And the most common type is the so-called lenticular array. So imagine you have just a normal TV, and you put a sheet of optical lenses in front of them. So optical lenses are pretty much the same thing that you put in your eye in contact lens to refocus light. And what these lenses are able to do is that they're actually sending light from different pixels on your normal TV into different directions of space. So they create a bunch of directional light rays. And when a viewer actually, look at the 3D display, a different image is going to come to his or her right and left eye, and therefore is going to perceive this so-called 3D stereoscopic effect. So the brain sees slightly different images and reconstruct the depth information about the image.
Because the key thing is that you've got to send a different picture to each of the two eyes for the brain to then recombine those and create the three-dimensional effect, haven't you?
Yes, so this is exactly correct. So people have been traditionally trying to do that using glasses. So glasses artificially, block one image or another in front of your right or left eye. But the trick here is to try to do this, without glasses. So your display must be able to send different images in different regions of space to reach, each one of your eyes.
Now, of course, the problem with doing this is that the computer or the display doesn't know where your head is and therefore doesn't know which bit to send to which eye. So how have you got around that problem?
Yeah, this is a great question. So essentially, you're right. The display doesn't know where you're located, and so we take the brute force, approach, where the display actually sends all possible perspectives, all possible images of the 3D object simultaneously, in parallel in space, so that any viewer, not only one, but you can have 10 viewers at different positions around the display, and each one of the viewers would have a different image reach his right or left eye, and so they would all be able to see simultaneously in 3D. So again, a brute force approach, just send all the images at once.
I guess that has the advantage also that if you move your head, you'll see around the object in the TV as well.
Exactly. So this is one of the very important points about our technology is that you can actually move around objects, very much like you could move around the hologram of Princess Leia in Star Wars that people like to reference.
David, can you talk us through then how you've achieved this clever trick? So just take us from the bottom up of a normal screen with its pixels and things. How do you get the effect you're achieving?
So our technology is very similar to liquid crystal display technology that is mainstream today in cell phones and your laptop screens. And the way these displays work is they have two parts. The first part is called the backlight, and the role of the backlight is to so you basically illuminate from the side with a bunch of lamps. They're called LEDs. And so the light propagates from the side of your backlight, which is a big piece of glass or plastic. And as it propagates from the edge to the center, it encounters a bunch of so-called scatterers. So imagine a bunch of little bumps on the surface of the backlight. And when light encounters such a bump, it's actually scattered from inside the backlight into the viewing zone of the display outside. So this generates a constant flow of light, and in order to form an image, you need a so-called modulator. And this is usually done using a liquid crystal front plane. So just imagine a bunch of little cells that can be controlled from completely transparent to completely opaque by just applying a certain voltage.
So how do you then get the light so that it's only going in a certain direction? So in other words, if you were looking at it straight at the screen, one eye is going to get information from one pixel area and another eye is going to get a different one. How do you control the direction of the light?
Yeah, and this is where our invention comes from. We replaced these little bonds I talked about that are present in traditional display. We replace them by nanostructure, which are called diffraction gratings, which are objects with features that are smaller than the wavelength. And when light hits one of these objects, of these diffraction gratings, it is scattered in a very directional manner. So it forms a light ray and in one particular direction. And then by changing the exact parameters of this nanostructure, we are able to control the direction at will. So we can create any light ray. We can send an image in any direction we want in parallel.
So can you change the direction that grid is sending light in, or is it fixed?
The directions are fixed, so they're set once and for all. And then the external modulator, your liquid crystal modulator, is able to change the intensity of this light ray. So
basically the computer's working out when to turn the light on or off, and it's directing light out of that particular pixel in a certain direction to effectively an eye or the other eye. And in that way you can get the two eyes seeing different amounts of light at the same time, and that enables the brain to be fooled into thinking it's seeing 3D.
Yeah, absolutely, and it can do so regardless of the position. And you could even be traveling around the display, and you would see a continuous update of the perspective. So you would seem like you actually are perceiving a continuous motion of the object in 3D.
So how long till I can buy a fancy smartphone and see pictures of my children in 3 dimensions on the screen?
As a researcher, I'm not really able to comment on this kind of commercial prediction, but I certainly, as a 3D display lover, I would want to see it as soon as possible. So I'm just going to work hard so that within a couple of years we can see the first applications one way or another.
Thanks, David. That's David Vital from the HP Labs in California.
And it's time now for our weekly look at planet Earth. And Richard Hollingham is looking at tidal energy this week. He met Judith Wolfe and Nick Yates from the National Oceanography Centre in Liverpool on a very foggy day by Liverpool's Albert Dock. And Judith began by outlining the potential energy contained in the River Mersey.
If we consider Liverpool itself, we have a 10-metre tidal range at Springs. That is one of the highest in the UK. Almost the highest in the world. That energy can be captured in various ways by running a barrage with turbines. The other kind of energy is the kinetic energy of the flow of the tide, and in straits and estuary mouths like here we can get really large flows which could be several knots of water speed, and that energy can also be harnessed.
10 metres?
That's between low tide and high tide, yes, on the maximum spring tidal range.
So potentially a phenomenal amount of energy there.
That's right, yes. The amount of energy you can get from a tide in an estuary is related to the area that's behind the mouth of the estuary, the area inside the estuary and the tidal range at the mouth.
Now, Nick, you were an engineer and you've been studying the potential of tides around the UK. What did you actually do?
The study in question was a computer simulation that took a computer model, and into that model we can see the tidal wave coming in, and then into the model we're able to simulate barrages in particular across estuaries, because as Judith said, the energy you get is proportional to the area and also the tidal range. And so the ideal place for a barrage to exploit tidal range, which is a physical structure which allows you to delay tidal motions and get a water level difference like conventional hydropower, and actually behind you, you can't see the other side, but the Mersey, you've got geography helping you, it's only a kilometre across. So for a relatively short physical structure, you can then place turbines in that and get, relatively speaking, a large amount of energy. So just to give you an example, for the Mersey, that would be something like a terawatt hour, which is a difficult number to get your head on, but you're probably talking somewhere between 500,000 and 1 million houses electricity from that one structure.
So how much energy could you generate in the UK from the tide?
We think it's going to be at least 20%. 15% from tidal range, with barrages over the major estuaries, plus 5% from tidal stream, which is from the fast motion of currents.
And what sort of structures? Like a conventional hydroelectric plant with turbines, or we see these wave generators with almost like sort of bobbing buoys going up and down.
Yeah, the structure for tidal range, if you like, it's like a harbour, actually. It's very similar technology. So you'd have rock, and then you would have probably concrete caissons where you've got turbines and sluice gates.
And what about the environmental consequences of putting something like that on an estuary like this one here?
Well, some of the environmental concerns are very much about intertidal habitats in estuaries. Estuaries are very productive areas and are very important for migratory birds and fish, particularly some of the mud waders and feeding birds on the estuary. Many people are concerned that the habitats that they exploit will disappear. One of the things we did in an earlier study was to actually estimate how we could best minimise that impact. If you run the barrage on the ebb and flood generation, you can actually modify the amount of habitat that's lost and minimise the amount that's lost.
Now, you looked at this across the UK, so different sites. Presumably some are more suitable than others.
Yes, that's true. I mean, for a tidal barrage, we're looking for the maximum tidal range, and the Mersey is particularly nice because it has a very narrow mouth, and therefore you would build the minimum length of dam across it in order to capture a moderately large amount of energy. So the energy would be relatively cheap here.
And so the dam wouldn't have to go the right away across the mouth, it would just go across a small amount?
It would have to close off the estuary completely, but the tide would still flow through the dam, through the sluices and turbines.
And how does this compare, say, Nick, with wind power and other forms of alternative energy generation?
The key thing with tidal, it is the renewable energy you can set your watch by. And so that predictability in particular is extremely important. It's funny, I was just reading recently from Ofgem some figures about the variability of wind, which went from 9 megawatts to 3 gigawatts within the space of 3 days. But that's not to say it's an either-or. I actually think we're going to need all of them, particularly to replace what we get from fossil fuels, but also if we move to electric vehicles, demand's going to go up.
Nick Yates and Judith Wolfe from the National Oceanography Centre in Liverpool. And you can find out more on our website from Planet Earth at nakedscientist.com/Planet Earth.
This is The Naked Scientist with Chris Smith and me, Dave Ansell. If you'd like to get in touch with any questions or comments, email chris@thenakedscientist.com, tweet @nakedscientist, or find us on Facebook.
The old floppy disks and even mini disks that are lying around in my office at home tell you all you need to know about how quickly new storage formats can become obsolete. But this problem doesn't just affect consumers. It also presents a big problem for archivists who are trying to store digital material into the future. According to Dr. Leo Enticknap, who's a lecturer in cinema from the University of Leeds, this is certainly a problem in the archiving of movies and television programmes, as he explained to Dominic Ford.
Now, we're used to hearing about classic episodes from the 1960s being burnt because there simply wasn't storage for the filmed with those programmes on. Surely, with the advent of modern hard disks and DVDs, it's much easier to store vast quantities of video information.
In the short term, yes, but, and I'm afraid there always is a but whenever we're talking about digital media. Firstly, you have a problem with chemical decomposition of the discs themselves. For example, in pre-recorded DVDs, the ones that are pressed in a factory, you can get into problems with the chemicals used to form the dye for the label on top attacking the substrate of the disc, for example, and causing problems. And with consumer recorded DVDs, DVDRs, for example, the recording medium is a dye, and that dye is very slightly changed in its light reflectivity characteristics by being burnt by a laser. The problem is that reaction that started by the laser being burnt can't be stopped completely. It can only be slowed down almost to the point of being stopped. So that dye layer is continuing to change very, very slowly even after it's been recorded. And as a result of that, basically your DVDRs have relatively small shelf lives.
So what timescales are we talking about here? If I burn a video onto a DVD, how long will it stay there?
There are a number of variables, but most archivists and librarians would not want to trust one for longer than, say, 3 to 5 years, and even that stored in optimal conditions.
What about hard disks? Surely those are more durable.
They're slightly more durable, but again, I'm afraid there's always a gotcha with all of these media. If you think about a hard disk, it's a complicated electronic and mechanical device. You've got 2 or more, sometimes several, glass platters which have the magnetically sensitive coating on them. You've got the head assembly. The platters themselves are on a spindle which has a bearing and which has lubricant in it. And on top of that, you've got a PCB which contains the control electronics and, of course, your interface to the computers. Think about all the possible things that can go wrong on that. You can have a failure of any one of these moving parts, which are incredibly tiny, and also you can have the issue of hardware or software obsolescence. What happens if in 20, 30 years' time computers quite simply don't have USB sockets on them anymore, in the same way that computers now simply don't have 5.25-inch or 8-inch disk drives in them as they did 30 years ago?
And I guess we've touched on the question of software here. Obviously, file formats are forever changing. Does that mean that you're having to continually reprocess this material into newer file formats?
Really, we're into some quite unknown territory here, because so far we haven't had a major instance of an audio or video file format in widespread use quite simply dropping out of existence in terms of being supported by the latest generation of playback software. But you never know, it could happen. I mean, just to give you a non-audio-visual example, if you have documents that were produced using only like version 1 or version 2 of Microsoft Word, and you try to open them using Microsoft Word 2010, well, it can be done, but you have to get involved in some quite complicated geekery in order to do it, involving downloading plugins and things like that. It won't do it straight out of the box. So even with probably the world's most widespread word processing system, if you're trying to open files that were produced using the version that was in use 15 to 20 years ago, you're going to have a struggle. In 20 years' time, a software manufacturer could be saying to itself, well, so few people now are still using MP3 that we're not going to push our production costs up by supporting this one. And yes, you could be in a position whereby it's going to be very, very difficult to reback that software format.
So this sounds like it's a problem not just for the media wanting to keep videos on file, but also for academics who want to keep documents that they were discussing 10, 15 years ago.
Yes, absolutely. I think archivists are going to have to keep their collections under absolute constant review and look to carrying out migration both in a hardware sense and in a software sense, as and when support issues really do start to emerge.
So what are companies doing to try and solve this problem?
There is no silver bullet. There is no widely accepted store and ignore format. In short, you've got a problem, and the moment you decide that you want to preserve this digital movie or this sound recording or whatever in the long term, you are making a long-term commitment to manage actively the integrity of that digital asset.
I guess this affects not only big companies who are making videos professionally, but also people at home. If you're shooting a video of your wedding, for example, what can you do to make sure that future generations of your family will be able to see that?
You've basically just got to do a scaled-down version of what the professionals do. You need to take ownership of that material and decide that you are going to make a long-term commitment to keeping it. What I do personally, for example, is that I back up all of my data to 2 separate portable sets of hard drives every week. One of them then goes into work with me on Monday morning and sits in my desk drawer all week, so that if my flat burns down, then I've got a copy of my data in another physical location. And I'm looking at constantly backing up, constantly keeping an eye on the currency of the file formats that they are encoded in. And to be honest, it's partly because I do worry about my ability to do that I still take most of my personal photographs on a Leica M3 film camera that I inherited from my grandfather, because I know that with a 35mm film negative, yes, obviously what I'll do is scan those negatives so I can email the photos to people and that sort of thing, but ultimately if I suffer a complete data loss disaster, I can always scan those films again. If the original is a born digital file and all the copies of that I have go, well then that's the end.
That's a technology that's been in use for over 100 years, so I guess you can be fairly sure that it'll probably still be in use in decades to come. I guess this has implications for how historians will look back on the 21st century. Some people have said that they will be overwhelmed with the amount of stuff that we record, but you're actually hinting that they will have a problem of not being able to read our records.
I think there will be that problem as well, and furthermore there's even a phrase for it which has kind of started to do the rounds in the archival community, and that is the digital dark age. And it's being speculated that just as we have lost, it is estimated, between 2/3 and 3/4 of the film shot during the first quarter of the 20th century, So we might end up in a situation whereby we've got this kind of black hole from, say, the first 1 to 3 decades of the digital era, where in fact very little survives.
That was Dr. Leo Enticknap talking with Dominic Ford.
It's quite scary what he was saying about the DVD lifetime, isn't it? I would have given it a good 10, 20 years, but 4 or 5 years, that's not long.
I guess everything is just so small that it just takes a very small amount of degradation to stop it being able to read.
I mean, I've got CDs that I wrote maybe about 10 years ago, which I was clearing up at home the other day, and I found these CDs, and they're definitely looking a bit dodgy in terms of the colour. They're decolouring and everything, and you think, I can see what people are getting at, because this was sold to us 10, 15 years ago as this is laser quality data that won't degrade. It's not true.
The other thing is that the readers are degrading. I'm not sure that a 10-year-old DVD reading device is going to work very well as well.
I think that's sort of what Leo's saying, isn't it? Anyway, the looming digital dark age that Leo mentioned does mean that archivists are searching for a store and ignore technology that's going to allow us to preserve digital data into the long term. But how? Well, one team from Harvard University, led by Professor Eric Mazur, has invented a process that can, they say, permanently store digital data inside glass.
So, Eric, how does this process actually work?
It works by taking extremely short but intense laser pulses and focusing them into the bulk of the glass, not on the surface, but in the bulk of it, and essentially creating a tiny void that can serve the same role as changing the dye at the surface of a DVD or CD.
But if you vaporise the glass on the inside, I don't understand where the glass that you vaporise goes to make the hole.
Well, if you take any material, it's made up of atoms, and atoms themselves are mostly nothing, right? The nucleus of an atom is tiny, tiny compared to the actual size of the atom. So in the lattice of any material, glass happens not to have a lattice, it's amorphous. But there's plenty of interstitial and other place to drive additional material. So basically what happens is that in that tiny little void that you've created with this super intense laser pulse, the atoms have basically been driven into the surrounding material.
So you get a little sort of hole which behaves like, you say, the pit that you would write into a DVD or a CD. So do you use the same sort of data encoding then to put the data into these little pits? Or are you using your own proprietary way of encoding the data?
No, we would use the standard technique. In fact, we've only demonstrated the technique. We've not gone as far as commercializing it. But you would, as a first step, simply use the same method that you use at the surface of a commercial CD or DVD. But now, instead of writing just a single layer, or in the case of a multi-layer DVD, maybe 2 or 3, you could write in the thickness of a standard CD or DVD 100 or more layers.
So how do you cause it to form these little pits inside the glass at a certain depth and not higher up? Because surely the light's got to go through some glass to get there.
Exactly. So the trick is in exploiting this extremely high intensity of light that occurs with pulses that have durations that are measured in what are called femtoseconds, millions of a billionth of a second. When you make your laser pulse that short, the intensity of the light becomes phenomenal. Right, because you're basically focusing the light in time, if you wish. If you now also focus it in space using a lens, you essentially put a whole lot of light on top of each other. You basically bunch up the light at the focus of this lens, both in space, transverse, as well as in time in the longitudinal direction. And as a consequence, the interaction of the light and matter becomes very different from the one we're normally accustomed to. If you take glass, for example, we use glass as windows because it's transparent, which means by definition the light is not interacting with the glass. It goes through it. But when you get to this exceptionally high intensity, and I'm talking, an intensity where the electric field in the light, because light is an electromagnetic wave, becomes larger than the electric field that binds electrons to atoms. When you get to that regime, you basically change the nature of the interaction between the light and the material completely, and you are actually able to rip apart the bonds between the atoms and deposit energy in that tiny little volume. It's tiny because it is completely limited to the volume where you focus the light. So if I place the focus of my laser beam not at the surface but inside the glass. I could not do this with a material that's not transparent, obviously, because then absorption would start at the surface. But if I take glass or plastic or any other transparent material, the absorption will only happen in that very tiny volume at the focus of the laser beam.
Eric, some people say that glass is a bit like a supercooled liquid, so it flows over time. Does this mean that the glass could move over time and occlude these tiny holes you've made in it, and then your data would disappear?
That is definitely true. Nothing lasts forever, right? I mean, we know that. However, there are certainly glass specimens that have lasted over 1,000 years. We still have glass objects from the Romans that is in very good shape. I think it would extend the lifetime of most recording media by several orders of magnitude. And I think 100 or several hundred years would be probably a safe estimate for a reliable readout of any data stored in this way. But
and I presume that the really good thing here is that because the data is being stored inside the glass rather than on the surface of the glass, like on the surface of a record, it means that surface abrasion or damage does not damage the integrity of the data, because you can read through that and see the message still written inside.
Correct. You could always repolish the outside to get a clean surface again.
So how much data can you pack into a certain area or unit area of glass?
Well, as I said, I mean, you can easily pack in 100 in a standard platter the size of a CD or a DVD. You could easily put 100 to 200 layers. So imagine putting the equivalent of 200 DVDs in a single DVD.
And have you had much interest from anyone saying that they'd like to try and use this commercially, or is this literally just rooted in the academic world at the moment as an interesting thing you can do?
No, we certainly have had interest. There's still a number of technological hurdles. One is that the laser that is used to write is not something that is the size of a laser that you would find in a DVD or CD writer. So this would not easily become a consumer item, but it could become an item for archival data storage. The other one is that writing the data is a lengthy process given the current state of femtosecond lasers, although that is improving dramatically over the past few years. And I could very well see that in a few years' time we could actually have a laser that could write 200 DVDs in a relatively short amount of time, meaning something like minutes rather than hours or days. The other problem is, of course, that right now magnetic and other type of semiconductor media are so cheap that writing the data in magnetic media and then copying them, if you want to preserve them, often is a more cost-effective technique than trying to exploit a new and as yet unproven technique.
Well, thank you, Eric. That looks like something to look out for in the future. That was Eric Mazur from Harvard University.
Now, it's not just new technology that could help us to store digital data in the future. Already, we compress some data so that it takes up a lot less space. And to find out how this works, we have with us PhD student Christian Steinrücken, who is from the Department of Engineering here at Cambridge University.
So, Christian, what exactly is data compression?
Data compression is really the art of communicating using less bits than it would usually take.
Where bits are the ones and zeros which all digital information is stored in.
That's right, using fewer units of information to communicate the same message.
So how do you reduce the number of bits you're going to use?
So the idea is really that one has to rewrite the message in a different way. And that rewriting can be made to exploit properties of the data that include, for example, long repetitions or statistical properties in such a way that fewer symbols are needed.
So if you have something which goes 101, 101 1,000 times, you could say, instead of writing 101 1,000 times, you could say, please write me 101 1,000 times, which is like one sentence rather than...
That's one way of doing it.
Do we use compression a lot at the moment?
Yes, compression is ubiquitous. Every smartphone has compression algorithms built in, and it's something that ships with every operating system at the moment. And it's really a technique that is vital for certain things to work at all. If you imagine, for example, the idea of a Mars rover on the surface of Mars, and you have limited bandwidth to communicate with that rover, you really are talking about a very expensive mission. You want to have the ability to get as much data back from Mars as you can. The bandwidth limit is not the camera on the rover or the instruments, it's really the satellite link. So the idea would be to compress the data as much as possible so that we can send more data overall.
So I guess there's two ways of compressing. You can either attempt to produce exactly the same output, or you can just try and get the important parts of the data.
Yes, both play a role. So there's a difference between lossy compression and lossless compression. Lossy compression is what's happening in JPEG, for example. The idea is that we throw away part of the data that we don't so much care about. And the other idea is to really preserve precisely the data that there are, but exploiting statistical properties to make them smaller.
So what are you actually looking at in your research?
In my research, I look at structural compression, which is the idea that certain mathematical properties of data can be exploited to make them really small. The idea is, for example, if you have sort of combinatorial objects, for example, multisets or permutations, that sort of thing. The idea is that there are mathematical properties of objects that surround us that can be exploited. For example, most data that we're dealing with are highly structured. That means that the surrounding sequence in a long sequence of text, for example, tells us a lot about the bit that we don't yet know. So when we're communicating a text or a long file, the idea that we've already seen part of the file helps us to encode the next symbol in a better way. So I look at compression algorithms that take advantage of such properties in files in order to make it easier to transmit larger files and make them smaller.
So if you really, really understand what you're sending, you don't actually have to send nearly as much.
Yeah, the idea is that if we already know which data we're going to send, then we don't have to send anything. The problem is making an algorithm that learns very quickly what the data is and gets a good idea of what is going to come and exploiting those properties that we learn. So it's really a form of machine learning.
So it's not just about a machine where you sort of turn in the handle, you put the data in and it comes out in a crunched down way. This is actually about the machine learning the pattern of the data in order to become better as it goes on at producing a more condensed or compressed output.
That's right. The problem is that at the time when the Mars rover is sending a file, the technology that's in it to compress doesn't yet know what the data is going to be. So it has to learn as it goes along what the data is to exploit those properties. At the receiving end, the receiver will learn in exactly the same way, and as data is decoded, will update its internal model in order to be able to follow along.
Does one have to send the code to the other so that I've compressed something and learned how I'm doing it as I go along? Do I need to send you the code I use so that you know how to unpick what I did and regenerate what I started with?
The idea is that we both use the same compression program, and when we start out, both compression programs are in exactly the same state. Now, as I start compressing a file, my compression program starts learning. It starts learning that certain names appear very often in the text. It may learn all sorts of other things. At the time when I decompress the file, the same process repeats. For the copy that is decompressing, it will also learn gradually as it decompresses what those names are. So the idea is that the compressor and the decompressor really have to be in sync. They are learning the same thing separately on perhaps different planets.
And is it just on Mars rovers, or are there other applications? I mean, we're going to compress the audio for this program, for example, and that means we'll throw away some of the things, some of the frequencies, some of the sounds that we don't think people are going to be able to hear or will not notice if they're gone. So could you take the similar sort of thing and make even better ways of compressing sound files so that our program isn't going to take up as much space on someone's iPod?
That's right. Whenever we have a better understanding of what properties we care about in the data, we can make a better compressor. And this is partially why there are many different file formats for audio, because every now and then there's a small revolution where an incremental change produces a better version or a better way of storing information. And so for audio, for example, something that happens in the MP3 format and other formats is that some of the frequency bands are thrown away that humans can't easily hear.
And that means that then you're saving space overall. You've thrown the data away, but you're never going to get it back, though. So that's an example of a lossy compression. Are you saying that your thing could be used in a way that will get back that sound we've thrown away?
I think it completely depends. Many sensors record things that we don't care about. But when it comes to things like electronic text, we probably want to preserve the exact text without changing it. when we decompress it. So this is a case where we really want lossless compression. Similarly, when we have executable files or computer programs that we may want to compress, or perhaps medical data, all sorts of things where it's really important to keep the precise file that we had to begin with, then we want to use lossless compression.
Brilliant. Thank you, Christian. That's Christian Steinrücken, who's currently completing his PhD in the Department of Engineering here at Cambridge University.
And finally, to bring the show to a close, Hannah Critchlow has been gazing into her crystal ball to imagine an apocalyptic future for computing.
This week, we contemplate a rather doomsday scenario.
Hi, my name is Martin Harris and I live in Cheltenham. My question is, we rely increasingly on computer networks. If a solar storm or malicious virus hit the network, could our current civilization's dependency on computer networks be damaged irreversibly?
So, could it spell the end of the world as we know it if all computers across the world crashed? Or could it lead to worldwide liberation? First up, what could cause our computers to conk? Listener Evan Stanbury from Australia got in touch with this.
A widespread computer virus could impact our computer networks temporarily, perhaps for hours or days. Geomagnetic storms caused by solar flares can damage the electricity grid and cause widespread blackouts lasting days or even weeks, especially in regions near the poles. High-altitude atomic explosions can cause an electromagnetic pulse that could shut down the electricity grid and fry the electronics in our computers, mobile phones and car ignition systems.
Not invincible then. And computers don't just sit on our desks, as Mike Muller from computers chip design company ARM explains.
There are lots of different types. They're in mobile phones, anti-lock brakes, TVs, traffic lights, railway signalling systems, and maybe the digital radio that you're listening to this on. And they're all joined together by computers in satellites and ones that run the internet.
So, what could the effect of a computer wipeout be? Stuart Coulson from the online security company Sakama said this.
I think the biggest fear would be medical devices. If they were to fail, well, that's loss of life straight away. Critical care patients, they're unlikely to survive. Alarm systems for vulnerable people, they're going to fail.
Plus, there's this.
Hello, my name is Jonathan Bowers. I'm the MD of UK Fast, an internet hosting company. I think the biggest area that would be affected would probably be the financial sector. There'd be no more international trade, same-day payments, things like immediate cash transactions or a stock exchange. We'd have, what you might call a socio-economic breakdown.
Plus, on the forum, listeners got in touch highlighting computer crashes causing mayhem on the roads, transport failures, system shutdown, and inevitable food shortages. But Jonathan also adds...
on a lighter note, evenings would be interesting with no more TV and an end to reality TV at last. So in that way, it possibly is a good thing.
Well, with that question digested, we move on to the next one. Jane wrote in with this.
How long does it take for a comet to completely melt away from repeated exposure to the sun? Will there come a time when all the comets are gone from the solar system?
So, since comets are essentially ice turning into vapour whilst orbiting the hot sun, could there be a day when all the comets have dried up and there's none left in the solar system? Send us your thoughts. You can tweet at Naked Scientists. You can write on our Facebook page, email chris@thenakedscientists.com, or you can join in the live debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow, and that is it for this week. Thank you to our guests, David Fatal, Leo Enticknap, Eric Mazur and Christian Steinrücken. Thank you also to Dave Ansell for joining me. The production this week was by Ben Valsler and Kate Lamble. We're off for a week to give us time to find all our Easter eggs next time, but when we return, we'll be tuning in to a show all about radio astronomy.